Hi everyone, and welcome to my talk, ScyllaDB Architecture Built for Speed. So I'm Zach Leviatan, VP Product at ScyllaDB. I love databases, I use them daily. Unfortunately, I don't have a cool hobby yet, but that's something I'm working on maybe next year. Unless you count bullet chess in chess.com. So what are we going to cover today? I'm going to do a quick run over Scylla architecture. And Scylla architecture can be, you can think about the architecture in layers. This is what I try to do in this session. I will try with the distributed aspect of the database. As you probably know, Scylla is a distributed database. Then we're going to zoom into a specific node and understand how these nodes work. And then we're going to zoom in even further and touch on the interaction between the node and the hardware. And this is where a lot of the secret sauce of Scylla is located, and this is where the great performance comes from. So let's get started. As I mentioned, from the high availability aspect. I want to map ScyllaDB for a newcomer to Scylla. I want to map ScyllaDB to other databases in the domain. NoSQL is a huge domain. There are probably hundreds of databases. Each of them have a different sweet spot. And Scylla, you can map the databases on two axes at least. One is the data modeling and one is a high availability. From data modeling perspective, Scylla is similar to DynamoDB, to Apache Cassandra and other databases. Sometimes people call this family of databases wide column store. I will explain in the next few slides what it means. And of course, there are many other type of NoSQL database, from key value to document store to graph database and time series and vector search and such. And I'm only going to focus on Scylla in this session. From a different dimension, you can categorize all the databases, and in particular NoSQL database, according to the CAP theorem that I'm sure many of the people here are familiar with. On this triangle, you can only get 2 out of the 3, as it say. So Scylla is tended toward availability. If you are familiar with the more advanced PAC-ELC or a module, which it doesn't replace the CAP theorem but add to it, Scylla prefer availability and consistency even if no node is down. And then I will demonstrate later, Scylla is actually great in low latency. And it achieves it by having tunable consistency. And all of that will be explained in a second. So if you didn't get all the terms right now, don't worry. So what is Scylla? As I mentioned, Scylla is a distributed database. It can be composed from 3 nodes to hundreds of nodes. Usually you won't need as many nodes because each node in Scylla can support a very high volume of requests per second, more than 1 million in many cases. So let's imagine that you have a 5-node cluster, in this case in one rack. The first thing you want to set when you start working with Scylla is what is the replication factor. What is a replication factor? Let's skip in backward for a second. A replication factor means how many times each information element is replicated across the cluster in case one of the node or 2 of the node are down. If you have a replication factor of 3, you still have one replica active and you can serve requests. This is how we get the high availability. So to set the replication factor per key space, this is the syntax. Create a key space, the name of the key space of course, and there is a class and replication factor. I'm not going to explain what is the class here in this session. Just take a look at the replication factor, which is 3. When the replication factor is set to 3, that means that every information element going to the database will be replicated on at least 3 nodes. And this is true if you have a 10-node cluster or a 20-node cluster or a 5-node cluster. If you set replication factor of 3, the data will be replicated 3 times. And let's demonstrate it. Let's say that I'm starting inserting information into the system. So I insert one row of information. It's located on node 1, 2, and 3. Second information element might be stored on different nodes. A third and fourth. And each information element is mapped to 3 replica in this case on the cluster, and the data, as you can see, is replicated in more than 1 node. So in this case, for example, if node 1 is down, there is replicas of all of the information from node 1 on other nodes. Actually, I'm colorblind, so I won't mention the color name here. And Scylla can be actually deployed not just in one data center. Very often, a user will deploy Scylla in multiple data centers. In this case, in this example, it's in the US, in Europe, and Japan. But we have customers that run even more than 3 data centers, run 5 data centers, 6 data centers. Often these data centers are deployed on AWS or Azure or GCP regions. So you have a very highly replicated deployment. Note that not all the data center need to have the same number of nodes. And you can actually set the replication factor per data center. So in this example, and this is by the way a rule of thumb, if you don't know much, use that. But in this example, I used replication factor of 3 on each of the data center, but it doesn't have to be the case. If on one data center you don't care as much about high availability, you can say, in this data center, I want only 1 replica of the data. Of course, you are taking a risk that if this replication fail, if one of the nodes fail, you basically lose a region. But maybe you have a replication in the other region and you don't care as much. The second point, after I hope everyone understood what is a replication factor. Anyone have a question about the replication factor? Please raise your hand. Okay, no one, and I cannot actually see you, but so let's assume you got it and move forward. And let's touch on consistency level. Consistency level is not part of the schema like replication factor. Rather, it's a parameter on each session or each request coming from the application to the database. As an application developer, you can determine what will be the consistency level of each request to the database, and let's demonstrate that. So let's imagine continue from the same cluster deployment as before with 5 nodes and a replication factor of 3 that I'm writing to the database from my application with consistency level of quorum. So how will that look like? The client send a write request to a node. In Scylla, and this is a little bit confusing for newcomers, in Scylla all the nodes are symmetrics. There is no primary or secondary node. All the nodes are exactly the same. But for each new session, each new request, the first node that gets the request is a designated coordinator just for this session. And of course, might be for other sessions, but not for all sessions. So if, for example, the first request will go to node W or node X, in this example, they will be the coordinator. So going back to assuming V is the coordinator, it's get the write request, it's check the replication factor is 3, it needs to send the write request or mutation, as we sometimes call it, to 3 different nodes. In this case, W, X, and Z. He sent the write request and waiting for ACK. In this case, he got ACK only from 2 nodes. So what do you think as a coordinator V should do in this case? He only got 2 ACKs. Should he return a success or failure to the client? Or maybe just wait for the 3rd node to respond? Okay, some of you guessed it right. Since the consistency level was set by the client to quorum, the coordinator only wait to 2 ACKs, 2 out of 3 is a quorum, before sending a response back to the client. At this point, the client got a success, but it's not exactly clear if node X was updated or not. In this example, the ACK message failed to get to the coordinator, but it could be that X actually didn't get the message, and X was down or didn't get the write request. You cannot, as a user, you cannot really be sure what the status of X is, but as long as you have a quorum of the nodes hacking and storing the data in a persistent way, you are good with it. By the way, there is an offline process to get X in sync with the rest of them that's called repair, which is out of scope for this session. Now let's see a similar path from the read perspective, but this time the read is done with consistency level of 1. Let's say that the client send the request again to a random node. This node acts as a coordinator, asking the rest of the node, 3 node, for the data. Only 1 response, but it's good enough because consistency level is 1, and the information actually sent to the client. And I won't get into it, but if you have the consistency level of the write and read more than a quorum, you guarantee consistency across multiple requests. This is why we call it tunable consistency. You are actually, as a developer, in control of which consistency you want to use. And note that consistency is trade-off for latency and availability. And why is that? Clearly, if I'm using consistency level of 1, the coordinator only have to wait for one node, so it will be faster. Many cases, by the way, the coordinator itself will be a replica, so it can send a response back to the client. But if you're using consistency level of 3, the data will be more consistent, maybe more recent, but if one of the nodes is down, you won't get a response. So depending on your use case, and even reading from the same table, you can have one application use higher consistency level, one application can use lower consistency level. Higher consistency level, more recent information, but less availability. And the same goes for multiple data centers. If we are going back to the example of having a data center per continent, often the application on a specific continent, in this case Europe, will use what is called a local quorum. Local quorum is similar to quorum that we've seen before, but it's limited to the local data center. And this is very useful because often the latency between different regions is much, much higher than the latency inside the data center. To give you some number to demonstrate it, latency inside a data center, inside the rack, is usually sub-millisecond. Latency between continent is often more than 100 milliseconds. So, of course, you want to use your read and write on most cases below a millisecond. But even if you use local quorum in a write, the replication factor can still include all the region. But what has happened that the other data center will be modify offline, so it wouldn't have to, the application wouldn't have to wait for the request. Everything will be done offline, and you basically benefit from two sides here. First, you get very low latency on your request, but you get across the globe high availability, which is also great. And this was actually, this architecture was actually tried by fire, if you will, a few years back. One of our customers got his data center burned down, which was tragic, but as far as I know, by the way, no one was hurt. But as you can see, and this is an actual screen capture from Grafana that used to monitor the cluster, out of 30 nodes, 10 was down in one data center, but the cluster continued to serve requests and got a great high availability. This is, I assume this is because the application used a local quorum, and not consistency level of all. Okay, and with that flash and fire, I can move to the next topic of data modeling. And in particular, I will try to connect the data modeling to the distributed architecture that we've seen before. And let's see if I succeed. So let's start with a query. And why do I do that? And this is actually typical to NoSQL database. When you try to model a schema, you always start with the query you want to ask the database. And you try to make sure the data model allow this query to run in a sub-millisecond, in Scylla case, in a sub-millisecond manner. This is slightly different than the way most people do it in a relational database when they do all the tables and relation just based on the data. On NoSQL, on general, you will start with the query, try to understand the query, and build the schema in a way that serves this query. So what is this example? This is, by the way, from an IoT use case, and you can Google Scylla IoT and probably find it very quickly. It's an imaginary use case. We don't actually have it in production. Imagine that we have a database that try to track heart rate of pets. So imagine each dog have a chip or something on the collar that report the heart rate and maybe more information every second. We store it on the database. And there are two queries that the owner of the dog or the pet would like to ask the database. One is, what is the latest heart rate? Or in other words, what is the current heart rate of the dog? Or the cat. I don't want to make cat lover mad as well. Another query is give me the heart rate across the last day or last hour, all the values, and then I can look at the max, min, do average, whatever. So this is the two queries. I won't go into the syntax of the SQL language, but if you're familiar with SQL, for example, it's pretty similar in syntax, a little more simplified. So how would I design such a use case? So I have a create table here that defines the schema. The patch ID will be used as partition key, and I will explain in a second what is a partition key. And the time in this case will act as a clustering key. And these are the two, mostly the partition key, but also the clustering key is the two main decisions that you have to make when you design a table in ScyllaDB. And let's see how each of them used. So first, the partition key. The partition key, that can be any data type. Scylla will take it and first convert it to a number. There is a hash function called partitioner. It's basically take every string you put in and return a number in a range. That's the first step. A second step is finding which node, or which nodes actually, because we have replication factor on the cluster, hold this information. And now you're going to hear for the first and last time in this session the term tablets. So you probably heard a lot about tablet in Door's session earlier, and you hear much more in other session in the summit. But for our perspective, it doesn't matter if you use vnode or tablet. The function of both is deterministically found which range of token or partition are on each node. So each node holds token ranges, not just one token range, token ranges. Can be defined by tablet or by vnodes. And all the nodes in the cluster, and often the driver as well, know which partition fit in which node, should be in each node. So once this is determined, every read and write with this partition will go to a specific node. This is why I hope it's clear why choosing the right partition key is very critical to your data modeling, because it's determined which node will host the data. And if, for example, your table always have the number 1 in the partition key, all the partition will be stored on the one node, and of course, or 3 node if you have replication factor of 3. And of course, you don't want to do that, because you want the data to be roughly evenly distributed across all the nodes in the cluster. So choosing a high cardinality, well-distributed partition key is a key element of good data modeling. And this is how it would look like. It would look like on the storage roughly. So you have partition. Each partition can be on a different node. In each partition, you have a list of rows, and the rows are sorted or ordered by the clustering key. If you remember earlier, we have a clustering key, in this case set to time. So all the rows in the partition are ordered by time. And this allows you to first, for example, if you put the last value in first, you can do ascending or descending order. Very easy to find the last heart rate of each pet. It's also very efficient to take a range, for example, last day of heart rate from a specific partition. And it still can be a sub-millisecond operation because the partition is local to a node. And so it's not a cluster-wide operation, and it's very efficient. So this was like basic data modeling in a few seconds, but there are many, many aspects to advanced data modeling. I'm not going to touch on all of them in this session. If you're interested, we're doing a Scylla University live later this year. You're welcome to get the session there. I do want to mention, just so you know it exists in Scylla, a few other options for advanced data modeling. So a few of them is materials view that I will demonstrate in a second. Secondary index, change data capture is a very cool feature that allows you to track update to the database and feed it to other microservices or Kafka or Redpanda or what's not. A collection and collection of collections, user-defined type, and time to live. Time to live you can define for each table basically how much time each element will live there, and you can also control it per session. Very useful, for example, if you want the data to live in the database just for a month and then expire. You can let the database manage it for you. So I'm not going to explain in detail how view and secondary index work. Just keep in mind that each of these solutions have its own trade-off. In materials view, you are duplicating the data to another table and let the database synchronize it for you, but the price you pay for it is in a write operation latency, because there is 2 operations for each write, and also, of course, in storage space. Secondary index, slightly different. Slightly different trade-off, but the high-level architecture is pretty much the same. So till now we cover, I want to recap what we did so far with my hand. So far we cover the high availability aspect of the database. Now I want to zoom in a little bit and explain how each replica works. Earlier we saw there was a coordinator. Coordinator sent a write request to 3 replicas, and now we're deep diving into one replica. We try to understand how this replica keeps the data persistent. So Scylla, like a lot of other databases these days, implement a log structure merge tree. And the way that it's worked, that every write request or every mutation to a node is written to 2 places. One is memtable, which is the primary storage in memory. And the second one is a temporary commit log, which will explain what it is in a second. Keep in mind that commit log is persistent. So if the node for any reason crash and restart, Scylla can actually rebuild the status from the commit log, because the mem table, of course, will disappear once the node restart. So mem table accumulate and collect rows. At some point, usually after a few seconds, the memory for this table is exhausted, and the mem table flash to an SS table on persistent storage. And an SS table is created. SS table is a data structure on disk. It's persistent. And the important thing about it, it's completely immutable. Scylla will never update an SS table. What it might do, and we'll see it in a second, is delete the SS table at a later point. But for now, imagine that a mem table flash to an SS table, the next mem table flash to an SS table, and you collect all the mutation on SS table on storage. Of course, at some point, if you really understand, you understand there is a problem, disk will be exhausted. So we'll touch that in a second, but before that, I want to explain about the read path. So the read path is slightly more complex because the data can be in one of many places. So Scylla first will check the cache. If the data is there, it can, or in the cache or in mem table, it can actually return a value pretty fast. Then it will check mem table and all the SS table on disk of this table. Take the latest value that it finds in mem table and SS table and send it back to the user as a response. As you can see, read is slightly more complex than write and have slightly higher latency. It's still usually sub-millisecond, but it's a more complex operation in Scylla perspective. There are many mechanisms like Bloom filter and indexes to optimize that. I won't touch it on this session. But I do want to go back to SS table and just explain very briefly what is compaction. So as I mentioned, SS table are accumulated on disk. Now keep in mind that this SS table can have the same value updated. So let's say that I'm updating my weight, which is always increasing and never decreasing. So on the first SS table, my weight is 80 kilogram. On the second SS table, I'm already 81. But the database actually only have to keep the last value that I insert. Doesn't have to keep both of them in most cases. So at some point, we want a compaction to merge this to SS table and take only the last value. And of course, this is exactly what a log structure merge tree do. At some point, it will take a subset of the SS table, read all of them, create a merge SS table, hopefully with less data than the sum of the previous SS table. Once the new SS table is created, it can safely delete the old SS table and the process continue. Of course, there are more SS table coming all the time, and compaction is an ongoing process that choose a subset of the SS table, merge them to a new SS table. And if you wonder which subset of the SS table to choose at each point, you have a very good point, because this what is called compaction strategy, and there are a few of them, and there are a lot of materials and information on what compaction strategy to use. Rule of thumb, just use the default Scylla provide for you. And if you want to learn more, we have a session just on that. So this was zooming to the OneNote. Now I want to zoom even further from my last part of this session and explain about the implementation. The implementation of Scylla have, I would say, one design goal in mind: good performance. But good performance can translate to many aspects. So high throughput and low latency. This is the two goals we try to achieve, and all the implementation or design decision that we made along the way try to achieve that. You have to forgive me for trying to summarize the optimization work that spent something like 10 years to a few minutes, but I do think that this will give you like an idea of what was the guideline when we started working, or when the engineers started working on Scylla, and most of these decision points are valid today as well. So C++, I don't want to get to which language is better, Common Lisp or C++ or Java or Rust. C++ is an enabler, if you will, to do memory management and storage management that we cover in the next session. Scylla keep everything async. So all the operation in Scylla are completely async. Developers are used to do async networking, but in Scylla case we also do storage in an async way, and that's important so we can have a shard per core architecture. And maybe this is shard per core is the most important aspect of Scylla. In many legacy system, I would call it's not legacy system really, it's new system as well, but system which don't care as much about performance use a thread pool. There are many threads competing for resources. At every second, one thread get in the CPU, run and doing stuff, then try to get to a memory, or try to get to disk, or try to do something which requires synchronization, get blocked, and the CPU will context switch it. We found that when we profile other databases, that actually this synchronization between the thread take the majority of the resources in many cases. So Scylla is built on a shard per core architecture, and shard per core is basically running one thread per CPU. But not only that, this thread has its own designated chunk of memory, designated chunk of network, and designated chunk of storage. So there is minimal interaction between the cores, and each of them can run its own engine in a very efficient way, because it's never get context switch, it's never get wait. And of course the development process or the development methodology does not use thread, because threads are pinned to specific core. And this is, I think, probably the most important decision point to get the high performance that you get from Scylla. It's also allows Scylla to scale linear with the number of cores. So Scylla, if you deploy Scylla on 16 core and then on 32 cores, you get exactly twice the performance. And if you go twice the cores again, twice the performance. There is no, since each core is independent shard, there is no almost no interaction between the cores, and you can actually scale with the number of core in a very efficient way. Lucky for us, you can get a very strong machine with a lot of core this day very easily on the cloud. So it's become super trivial to use a large machine or large VM, and you can a cluster that on other database require 100 nodes, with Scylla, which is more efficient, can take like 20 small nodes or just 3 large nodes. So all the administration become much easier. And actually, at least on the cloud, the size of the node also comes with better networking, so it's actually not a bottleneck, and it's really linearly scaled by the number of cores. I think I touched on this aspect as well. Scylla, I just want to mention that Scylla is NUMA friendly. You probably ask yourself, what is NUMA? So on latest hardware, the memory is actually not evenly reachable, if you will, from all cores. It's physically closer to some of the core on the machine, and other part of the memory are close to the other part of the core. Since I already mentioned that in Scylla each core have its own designated memory, or each shard have its own memory, we can and we did use the closest memory, physically closest memory to the core, so every access to memory by a CPU is much faster because the memory is closer. We can take advantage of such feature because we use a shard per core architecture. I'm speeding a little bit ahead, but all of this is covered in much more details in Scylla University and other places. Scylla also have a unified core, and definitely not use AMAP. There is a great talk on why AMAP is probably not a good idea, explaining much a better way than I could ever do. So go there and find this article and read it if you're interested in that. Last topic I want to talk about is how Scylla leverages storage, and in particular SSD. So running an efficient read and write from storage, of course, is critical for a database, because a lot of what databases are doing is reading and writing from storage. To make it as efficient as possible, Scylla actually doing a quick benchmark on the storage and found the sweet spot for reads and write. And when I mean sweet spot, I mean the number of concurrent requests that make the best performance, lowest latency and higher throughput. If you would try to write more concurrent requests to the storage, everything will work, but the SSD will simply queue all the requests internally. We don't want to get there. Why? Because then we have no control on priority of the queues. And the Scylla, and especially the sister framework that implements Scylla, or the infrastructure that Scylla built on, want to manage all the queues by itself and give them priority. So for example, we can give higher priority to the commit log and maybe lower priority to the compaction, and it's all dynamic and depending on what the database wants to do, but it have full control of the storage scheduling, and this is why we can get such a great performance out of SSD. It's also allow us to expose the scheduling decision to the user using a feature called workload prioritization, which is part of Scylla Enterprise. In workload prioritization, you can actually affect the scheduling, not directly, but you can affect the scheduling of Scylla. And a typical example will be that you have two kind of workload on the same database. One is real-time or OLTP. One is not real-time, analytics or OLAP. You want to keep the real-time under 1 millisecond, and you don't care as much about the analytic time. So in analytic query, usually ad hoc query, you don't care as much if it's 1 second or 2 seconds, while you do want to keep the real-time request under 1 millisecond. So in Scylla, it's straightforward to do that using workload prioritization. You can set different workload prioritization for each workload, and by that give priority, for example, for the real-time request. To summarize this part of the session, we implemented a bunch of design decisions to make Scylla with high throughput and low latency. But as the full disclaimer earlier, there are many performance improvement and performance work along the years, and we continue actively working on it. Latest Scylla Enterprise actually much better performance than previous one, so it's an ongoing effort. And a quick way, if you want to see it yourself, we have a quick demo that you can run on Scylla Cloud using Terraform, which using 3 nodes can get easily to 1 million requests and even more than that. So if you want to run it really in a few minutes, you can use this example. I gave the link here using Terraform, and thanks Attila for creating it. So to summarize, Scylla is built for high availability and big data. Using latest and greatest hardware, we can get great performance, and by great performance I mean high throughput, which translate to a lower number of machine and less money you spend on the cloud, and low latency, which translate to better servers. We also expose internal scheduling so you can control them through workload prioritization. And I won't get into actual comparison with other databases, but believe me, and if you want, you can find the benchmark that this performance gain can be translated directly to savings. And with that, I want to thank you. I will be in the chat later So thank you very much, and stay around for other session in Scylla Summit. Great to see you here.